Increasing the number of resistors in a series circuit will increase the total resistance of the circuit. Now, this is because in series, charge carriers would have to pass through all of these resistors and lose energy. So the more resistors we have, the more resistance the charge carriers all have to move through. For example, let's suppose we have two circuits that use the same type of resistor. On the left, there is only this one resistor, which let's say has resistance R. As this provides the only resistance in the whole circuit, then there is a low total resistance. Then on the right, we have three of these resistors, all with resistance R, like we had in the first circuit. But here, all these resistors combine together to make a high total resistance. But how exactly do we find the total resistance of a circuit? Well, the total resistance of components in series is the sum of their individual resistances. So in other words, we just find the total resistance in series by adding together the resistance of each component. So if we had a series circuit with two resistors, one with resistance R1 and the other with resistance R2, then we can say that the total resistance, or R total, is equal to R1 plus R2. This means the total resistance depends on the size of both individual resistors. This is why we design ammeters to have as small a resistance as possible, so they don't affect the total resistance. For your exams, you need to be very comfortable using this equation. So let's try an example with it. A series circuit consists of a cell and two resistors of resistance 4 ohms and R respectively. Given the total resistance in the circuit is 22 ohms, calculate the value of R, where we've also been given a diagram of how this circuit is set up. This is quite a simple problem so long as we know the rule for resistors in series. So step 1 is to rearrange the equation for resistances in series to make the unknown resistance the subject, where this equation is R total is equal to R1 plus R2. In this problem, we're told one of the resistances is 4 ohms and the other has an unknown resistance R. So to find R, we need to take the total resistance and subtract the resistance of the 4 ohm resistor. Now in step 2, substitute values into the rearranged equation to find the unknown resistance. So in our rearranged equation, the total resistance is 22 ohms and the resistance of the other resistor is 4 ohms. So the unknown resistance is equal to 22 minus 4 ohms, which equals 18 ohms. So that's how adding resistors in series affects the total resistance. But how would it affect the current of a circuit? Well, increasing the number of resistors or components in a series circuit will decrease the current through it. Remember that the current in a series circuit will be the same everywhere. Then the size of this current is determined by the total resistance in a circuit. Let's look at two more series circuits, this time comparing the size of the current that would be flowing around them. We'll be using the same cell with the same potential difference to power both circuits and a set of identical lamps. In the first circuit, we only have one lamp with resistance R. So we have a low total resistance in the circuit, meaning a high current will flow around it. Then in the second circuit, we have 3 lamps with the same resistance R. By adding more components, we have a higher total resistance in the circuit, and hence a lower current, since we also have the same potential difference supplied. The fact that we used lamps for this circuit means we don't even need to use an ammeter to compare these currents. Since there is a higher current in the first circuit, more power is supplied to the one lamp and it shines brightly. Then in the other circuit, the lower current means less power is given to the lamps and they are much dimmer. But what about the potential difference? How does the resistance in a circuit affect that? The potential difference from a cell is split between components depending on their resistances. So let's consider a series circuit with a 1 ohm lamp and a 5 ohm resistor, both of which are powered by a 24 volt cell. Remember that in series circuits, the sum of the potential differences across each component must equal the potential difference from the cell. But using knowledge of series circuits, we can deduce that these potential differences must be in the same ratio as the resistances. In this case, the lamp must have a potential difference of 4 volts, and the resistor 20 volts. This adds to 24 and is also in the ratio of 5:1. The reason we can do this is because it's the same current flowing through both components, though you don't need to be able to explain this in your exams or make use of these ratios. The main thing you need to know is that in a series circuit, a component with a larger resistance will get a larger share of the potential difference. However, you can still be asked to do calculations that combine all the rules for series circuits. So let's try an example of this now. A circuit consists of 2 lamps in series powered by a 12 volt battery. One lamp has a resistance of 6 ohms and the current through it is 1.5 amps. Calculate the total resistance in the circuit. And again, we've been provided with a diagram to help us visualize the problem. There'll be a lot more steps involved in this one, with various rules and equations we'll have to recall. So first, let's calculate the potential difference through the first lamp. So that's this lamp we've been told the resistance and current for. We'll need to use the equation V equals IR, or potential difference equals current times the resistance. So the potential difference of this lamp is 1.5 times 6, which equals 9 volts. In step 2, use series circuit rules to determine the current and potential difference for the second lamp. So that's this lamp here, which we've been told no information about. But using our knowledge of series circuits, we'll find we actually know everything we need to state a current and potential difference for this lamp. First, remember that the current in a series circuit is the same everywhere. So in other words, I1 equals I2. This means that the current through this lamp must be the same as the first lamp, which is 1.5 amps. Then the potential difference of each component must equal the total or supplied potential difference. So VT equals V1 plus V2. In this case, the potential difference of this lamp is the potential difference of the cell minus the potential difference of the first lamp. So that's 12 minus 9, which gives us 3 volts. Then in step 3, rearrange the equation relating resistance, current, and potential difference to make the resistance the subject, where we'll be using V equals IR again. To make resistance the subject, we should bring current over to the left by dividing both sides by I. This gives us V over I on the left and just R on the right. With this, we can complete step 4, which is to use the rearranged equation to find the resistance of the second lamp. If we swap the left and right sides of the previous equation, we'll have R equals V over I. And using the series circuit rules, we find that the potential difference of the lamp was 3 volts and the current is 1.5 amps. So the resistance is 3 divided by 1.5, which is equal to 2 ohms. Also notice that the resistance of this lamp is 3 times smaller than the first lamp, and the potential difference is also 3 times smaller. Now the last step is to just calculate the total resistance of the series circuit, where we'll need to use the rule R total equals R1 plus R2. In other words, we add the given resistance with the resistance we've just found. So this is 6 plus 2, giving a total resistance of 8 ohms.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy-to-follow videos, and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!